This is Mrs. O'Neill for Chapter 2, Section 3, Elements and Compounds. So in this section, you're going to be able to explain the difference between an element and a compound, distinguish between a substance and a mixture, and identify the chemical symbols of elements and their names. So take 2 pounds of sugar, 2 cups of boiling water, and 1/4 teaspoon of cream of tartar. You have the ingredients to make spun sugar. Add food coloring and you have the sticky sweet concoction sold at baseball games and amusement parks known as cotton candy. Sugar is a substance that contains 3 other substances: carbon, hydrogen, and oxygen. In this section, you will learn how substances are classified as elements or compounds. All right, so now let's look at some of this information. We have carbon, we have hydrogen, we have oxygen. That's the formulas. Carbon C, H2 would be hydrogen, and O2 would be oxygen. And we're going to talk in more detail as to why certain elements have this subscript as a 2, considering a diatomic molecule, versus other elements are just its symbol alone. So we'll talk about that. So these are elements. Together, they form sugar. Well, sugar's formula is C6H12O6, and that's a compound. So we have 3 different elements combining to make one compound. That's going to be considered a chemical reaction. So pause the video, fill in the notes, and then play to hear my words. An element is the simplest form of matter, and every element has very unique properties. So here we have mercury, which is a liquid metal. Pretty cool stuff. Looks silverish or gray, but it is a liquid. It is the only metal only metal that is liquid at room temperature. Carbon is this black stuff, but carbon also exists as that beautiful diamond that women adore. And of course, copper has that unique copper color. And all 3 of these have different or unique properties because of the atoms that make them up. Just like the Parker 51 pen has this erythrium, something that you probably never heard of, but erythrium is an element on the periodic table. So a compound is a combination of 2 of those elements, 2 or more, I should say, elements combined. But we want to remember that a compound has to be a fixed ratio. So in other words, this is water, H2O. But if we change the subscript of H2O to H2O2, now we formed a different combination of that fixed ratio, and now it becomes hydrogen peroxide. It is a totally different substance. So we want to remember that every compound has a fixed ratio of those elements to make it that particular pure substance of a compound. Same thing with NaCl. If we have any other combination besides one Na and one Cl, we will not have salt. It would be something else if it exists at all. So a chemical change is a change that occurs that produces totally different matter. And we're going to go through a couple of examples here. These are examples that you can write down, but we're going to go through some of those examples in a little bit more detail as to what I mean by changing the matter altogether. So distinguishing between elements and compounds is sometimes not that easy. So if we're breaking down a compound, something like here, we're going to break down some sugar. It says a chemical change is a change that produces matter with a different composition. That's a big thing that we want to remember, a different composition. So if we take some table sugar here and we heat it up, it goes through a series of chemical changes. The final result is here, this solid carbon and white vapor. It's hard to, water vapor. It's hard to see it, but there's probably some smoke coming off of here as well, which would be water vapor. So we started out with one compound, which is your sugar. We added heat, that's what this triangle is for, and we produced 2 other substances, 2 totally unique substances. And one thing we can think of is that the names are totally different as well. So we have sugar with some heat makes carbon, that doesn't sound like sugar, and water, well, that doesn't sound like sugar either. And what does this little S's and this G mean? Well, the S's represent that those are in the solid phase, and the G represents what's in the gas phase. And again, this is something that we're going to learn more in detail later on in the course. This is also what is known as a decomposition reaction, because we're taking one reactant and we're breaking it apart. We're decomposing it into multiple things. So that's known as a decomposition reaction. Again, something we're going to learn later. The more I can give you now as far as a preview, the more, or I should say the easier when we actually learn it, it's going to be. So here's another example. We have sodium. Again, Na is an element because it is one capital letter with one little guy, so that's sodium. And this S tells us that we're starting it in a solid phase. So sodium is actually stored under oil to keep it from reacting, usually pretty violently, with oxygen or water vapor in the air. So then sodium vapor, though, this is sodium vapor here, produces the light in some of the street lights. So if you see a street light that kind of looks a little off or a little bit more on the orange tinge, it probably has a little bit of sodium in it. Then we can take some chlorine. Here's another element. I know it's an element because it has one capital letter, but it's called a diatomic molecule because of this too. And the G tells us that it's normally in room temperature is in the gas phase. So chlorine, though, is used to kill harmful organisms, especially in swimming pools. So now let's look at this combination reaction. So we have sodium, we have chlorine, we have two elements, and when they combine, this is called a combination because we're taking multiple things and we're putting them together to make one thing. In this case, sodium chloride, salt, we're having a combination reaction. So it's commonly known as table salt, and it's used for seasonings or to preserve food. So again, if we look at this reaction, we took two reactants, one solid phase, one gas phase. We combined them to cause a reaction to bring them together to make a compound. How do I know this is a compound? Two capital letters. Again, some of this is just a preview. You just need to be able to know the difference between the element and a compound by looking at capital letters or on the periodic table. So we will be going more in detail about the flow chart, and I do believe even in your notes towards the end of the section, there's a place to write it, but I have it a little bit later when you have to put it into your notes. But if we look at this flow chart, it's a nice flow chart because everything is matter, and we can break it apart into two components, a substance or a mixture. Well, a substance can only be two things. It can either be an element or a compound, and a mixture we also divide it into two categories, homogeneous versus heterogeneous. So again, we're going to come back to this flow chart in a minute. But now let's do some practice problems. Can you distinguish between these three things, which one's an element, if there is one, which one's a compound, if there is one, and which one's a mixture, if there is one? And of course, you also think about the reasoning. Give a reason why it would be classified as that. So pause the video and see if you can come up with some answers. Hopefully you wrote something down. Hopefully at least you got to pick between element, compound, mixture, and hopefully you went above and beyond and wrote some kind of reasoning, the why. So number one, it's a compound. First of all, I'm showing you the formula, and the formula shows you two capital letters. So that is a big, big hint that it's a compound. Two or more capital letters, that must mean I have two or more elements combining. Salt water, well, salt is a compound and water is a compound, so we're going to call this a homogeneous mixture. Or we could also call it a solution. Remember those two things. So we want to remember that it's two things combining, in this case two compounds, and together they make that solution because it's the same throughout. And sodium, hopefully you know by now that that's an element. It has one capital letter and it's on the periodic table. So it's only going to have one kind of matter. So chemical symbols we've talked about before. You've learned them through your summer assignment. So again, we have all of these elements as examples, and all of them have one capital letter. And if there is a second letter, it is always lowercase. A chemical, however, or I'm sorry, a chemical formula or a compound, I should say, has multiple capital letters chemically combined in some way. And again, it has that fixed ratio, right? That ratio is always going to be the same. So if you need aspirin, this is the ratio of those elements you need. So symbols started way back in the day. They were used to represent elements, but they've changed over time. And actually alchemists, and we'll talk about those later, actually used to use drawings for some things. So not only did they use drawings or letterings for elements or like the alphabet, but they also used certain elements to represent certain words. So today, however, is only 1 or 2 letter symbols that will represent those elements. So we did talk about Latin names a little bit, at least I hope we did, especially when we talked about iron, when we talked about Fifi and Ferris from the Iron Pigs. They use the word ferrum here, but sometimes it is considered ferrous. You do not need to know these Latin names, but just be aware that that's why these symbols are really weird compared to the name that we're used to, and it's because those symbols come from the original Latin name. So the periodic table, again, is arrangement of these elements, and they're arranged in that order because they are based on the element's properties. And when we get to the periodic table chapter, we're going to talk a little bit more in detail why the groups are called the way they are, why the periods are the way they are, why these elements are arranged the way they are. So groups are those columns. There are 18 total, and some have their own name. Why? Because they have such similar chemical and physical properties that sometimes they're known as families. So sometimes you're going to hear them as groups, and sometimes you're going to hear them as families. So think about your last name. Sometimes your name, your last name anyways, represents your family name. I belong to the O'Neill family. That's my last name. Periods, however, are the rows, and there's only 7 of them, and we're going to talk in more detail about those last 2 rows and how they are truly part of period 6 and 7 in the main periodic table. And again, these periods allow those properties of those elements to be repeated. So again, they go across. Periods come at the end of a sentence, so periods are rows to me. So here's some more, again, diagrams, because I can't show you atoms and molecules, but I can show you models. So I got a bunch of dots here. What is it? Element, compound, mixture. Hopefully you came up with element. All right. Ooh, now I have 2 small dots with 1 big dot. What is it? An element, compound, mixture. You got it. Compound, because they were all the same. Ah, but now we have some big dots. We got some small dots. Some are white, some are blue. You better believe that it's a mixture. So hopefully you can see the difference between an element, a compound, and a mixture. So this is that flow chart. Make sure that you write these in your notes. There might be room to write some diagrams as well as far as the on the molecular level. So again, here's some visuals of what elements look like, what compounds would look like, and what mixtures would look like. Again, pause and make sure you're really understanding what it would look like on the molecular level. So in your notes as well, put one of these examples. Again, this tells you the example, this tells you the why, and maybe you might want to draw something for example of an element, an example of a diatomic molecule, and again, we'll talk about this more in detail later, but some elements do not exist on their own. Some of them have to be connected to each other in order to exist. Again, some more examples of diatomic diatomic molecules, and some others like phosphorus, even though we write it as P, really exists as P4, and sulfur exists as S8. Here's an examples of compounds. Please write one of those down. Here's an example of a homogeneous mixture. Again, write one of those down or come up with one of your own. Here's a heterogeneous. Again, you only need one example. So you ready for that quiz? Pause, read, and hopefully you come up with the right answer. Hopefully. Number 2. Did you come up with that? Because these guys are names of compounds and air is a mixture of all kinds of gases. and number 3. Hopefully you got that one right because of your summer assignment. All right, we'll see you in class.